In today's lesson, I want to talk to you about tectonics. So let's go ahead and just jump right in. We discussed on day one that Earth is essentially a synergistic group of systems. So all of those systems tend to kind of work with their own components, their own parts, but then they also influence each other. And we're going to hold on to the climate system for a couple of lessons, but today I really want to focus on the geodynamo system here and the plate tectonic system here. In order to do that, we need to first remind ourselves that the Earth is made up of different layers. So we're going to talk about those different layers, specifically the inner core and the outer core. The deep mantle, which we'll call the mesosphere. We'll then talk about the fluid convecting part of the mantle called the asthenosphere. And then we'll talk about kind of the rigid upper layer called the lithosphere. So we'll deal with the climate system later on, but really we want to talk about kind of how we figured out the plate tectonic system. And a lot of that has to do, believe it or not, with what we now know about the geodynamo system. So first off, let's talk about how we differentiate the Earth into layers. And there's two different ways that we can do this. If we break up the planet into layers, we can do it by two ways. One is if we separate the Earth by the layers that have different physical properties. For example, which ones are rigid and which ones are fluid. Or we can break up Earth into layers based on their chemical compositions. For example, which ones are felsic, which ones are silicate, which ones are metals. So we'll kind of start by doing this in each of the ways first. So let's talk about breaking up the Earth into its layers based first on its chemical composition. This is kind of the easiest way to do it because if you do it by chemical composition, you get three main layers of the Earth. You get the crust up here, you get the mantle here, and you get the core here. Okay, so the crust is mainly made up of silica minerals, which you learned in yesterday's lesson are called silicates, but mainly they are light felsic, right? Felsic silicates. So things like granites and whatever else. The reason, remember, we're separating these by chemical composition. So while these are silicates, the upper part, the crust, is made up of felsic silicates. The mantle is also made of silicates, but these are made up of ferromagnesian silicates. So those are minerals like olivine and those silicate minerals that have a lot of iron and magnesium in them. And of course, this should make sense too, because the dense minerals are going to sink further into the planet and the lighter minerals are going to stay up at the Earth's surface. So now you've got felsic silicates at the Earth's surface, ferromagnesian silicates for the mantle, and the core, last but not least, is going to be made of metal. And specifically, the core is made up of iron and nickel. Some sulfur, but essentially we have now a metal core that is made up of iron and nickel. So if you were going to separate the Earth into its layers based solely on composition, you would have three layers: the crust made of felsic silicates, the mantle, ferromagnesian silicates, and a metallic core. If we then instead separate the Earth based on layers that we separate out by physical properties, you're actually going to have 5 different layers. So let's look at the different layers that we can do using physical properties. Okay, we're going to start at the bottom. Okay, whereas we had the core before, we now can separate the core into an inner and an outer layer. The inner core, even though it is metal, is solid, and the outer core, still metal, is fluid. And specifically what that means is that the outer core can convect. So we have a fluid outer core that the metal is able to convect. So that's the two pieces that we have now. You have the inner core, which is solid, the outer core, which is fluid. Now we're going to get up into different parts of the mantle, and we're going to have 3 main layers here. So we're going to have the mesosphere. It is relatively rigid, right? It's going to be kind of a rigid layer here. so it does not convect very much. Now we're going to have the upper two most layers, the asthenosphere. This is plastic or fluid, which means once again it can convect. And the rigid layer above it is called the lithosphere. Remember that litho means rock, right? And so the lithosphere up here that's sitting on top of the asthenosphere, the lithosphere is going to be a strong, rigid, non-fluid layer. So once again, we can separate the Earth into 5 layers if we use biophysical properties. You've got now inner core, solid metal, the outer core, fluid convecting metal, and then the 3 layers of the mantle, which essentially are the rigid mesosphere, the fluid asthenosphere, and the rigid cold lithosphere. So keep those in mind because I'm going to use some of those terms as we start to develop the theory of plate tectonics. I know you've talked about plate tectonics probably in high school science classes, probably in middle school science classes. And one of the reasons why the theory of plate tectonics is so important is because it really does explain a bunch of what we see at the Earth's surface. It explains why mountains are where they are, where we get earthquakes and volcanic hazards. And it even explains how we can have plates that are moving around the Earth's surface, but we don't actually see the planet getting bigger. In fact, what we're doing is we're recycling the rigid lithosphere at the subduction zones. So it's a really important theory. And remember from lesson 1, when we say that plate tectonics is a theory, we're using the definition of a scientific theory. This does not mean that, well, it's a guess or, well, it's something that we're unsure about. Instead, a scientific theory is something that we definitely see repeated and observable evidence for, and that the data seem to support at the present time. So I want to talk to you a little bit about how the plate tectonic theory came about, because believe it or not, it was only in the mid-1960s. And that was only the decade before I was born. And so you can imagine that, for me, plate tectonics is relatively young in terms of its history. But in the early, 1900s, before we had plate tectonic theory, this gentleman here on the right, this is Alfred Wegener, he came up with an idea about why the shapes of continents were the way that they were, based on something that he called continental drift hypothesis. Now, remember from our discussion of scientific terminology, continental drift hypothesis. A hypothesis, remember, is something that needs to be tested, right? Continental drift, the idea that Alfred Wegener came up with in 1915, was not put into a theory. In fact, a lot of the data that was collected after Alfred Wegener came up with this idea actually disproved it. And so plate tectonics is the kind of new and improved theory that we have now, based on a lot of the observations that Alfred Wegener made when he came up with continental drift hypothesis. So what was this idea? Before continental drift and before plate tectonic theory, many people believed that the continents were fixed during the formation of the Earth. They didn't necessarily know that plates or continents were able to move around the planet. And it wasn't really until Alfred Wegener started to make some observations that the idea that the continents could move at all was even entertained. In 1915, Alfred Wegener was up in Greenland, and he actually was doing some meteorological surveys, and he was noticing ice flows in Greenland, and specifically how ice flows would kind of break up into different pieces. And the pieces would actually have the shape of what they looked like when they were once connected, but then those shapes would start to kind of move away, retaining the shapes of when they were still connected. So what he came up with was this idea that, well, when he looked at a map of the continents, continents actually looked like they would fit together like pieces of a puzzle if they were able to move back to where they were touching each other. Very similar to how you could fit those pieces of ice flow back together like a puzzle after they had drifted apart. So Wegener's continental drift hypothesis suggested that maybe the continents are moving and that the continental crust, the actual pieces of continent that we see on the map, are plowing through the oceans, almost how an ice-breaking ship would plow through a frozen ocean. Remember, Wegener knows what he knows, right? He knows what he sees in his scientific world. And so when he sees a ship breaking through an icy ocean, it makes sense to him that, well, maybe the continents are breaking through the rigid ocean floor as the continents are moving around. So the observations that he had literally were what he was seeing in Greenland during his surveys. He was seeing these ice-breaking ships. He was seeing those big plates of ice that had just broken apart, but yet still retained their shapes from when they were once connected. So he started to come up with this idea that, if these ice floe pieces once fit together, maybe so did the continents. So he started looking at some maps and some observations from around the world to see if he could create some data that would support continental drift hypothesis. The, I think, biggest observation that he made was that if you take all of the continental land masses right now, that if you kind of put them all back into one big supercontinent, they do fit relatively well. If you're using, kind of the examples here of, say, here's North America. Ooh, you can't see yellow. Here's North America over here, right? Here's Asia and Europe. Kind of they do fit pretty nicely together. I think the two that are very easy to see is kind of this part of Africa sits very nicely kind of right in here with South America. So looking at a map, Wegener said, the continents do look like little puzzle pieces. And we could certainly see how the shape of one could kind of just fit very nicely into the shape of another, suggesting that, yeah, the continents have drifted to their current locations, but maybe they were once connected in a supercontinent that Wegener would later call Pangaea. What he also did was take all of the continents and kind of move them back together, so kind of retrofit them into one large supercontinent, this idea of Pangaea. And when he did that, what Wegener noticed is that at certain times in geologic history, rocks of the same age showed very similar climatic belts, climatic regions that matched up beautifully when the continents were put back together. For example, the southern parts of South America, Africa, India, Australia, and Antarctica, around certain times, say the Ordovician period, all of them recorded glacial conditions in Ordovician rocks, and those could have been all connected at the same time during the Ordovician. Remember, India right now is way up here, right above the equator, so very unlikely for it to have huge glacier deposits. Same thing with the sub-Saharan Africa right in here. Unlikely that it would have glacier deposits. However, if you moved everything southwards and kind of huddled it up and attached it to Antarctica, you notice that they would all be sitting around the South Pole and they could all have very nice glacier deposits lined up nicely. They also would notice too that you would have nice kind of tropical belts sitting right in here that could have all been sitting at the equator at the same time. And even too, right, desert belts sitting up in here and then desert belts here kind of south of the tropical belts. So these evidences of past climates, these belts of climate really only line up very nicely once you put the continents back together. Another thing that he noticed is that if you put the continents back together to where they fit most appropriately, what you would notice is that there were certain fossils, certain organisms that were found on continents that are now separated by huge oceans. But if you put them back together, you would notice that those same fossils would end up becoming very close to each other. For example, this is a fossil here. This is called a mesosaur. And if you notice that here, mesosaurs are found in Africa and South America. Right now, Africa, South America are separated by a huge Atlantic Ocean. Now, Mesosaurus is an aquatic reptile, but it's not an ocean swimmer. In fact, it used to live in rivers. And so it's very unlikely that with South America and Africa being separated by an Atlantic Ocean the way they are right now, that these mesosaurs could have swam across, the South Atlantic Ocean. Instead, it's probably more likely that Africa and South America were once attached, and the mesosaurs were actually able to exchange across the two continents. My favorite little guy is this guy down here. This is Lystrosaurus. And you can kind of tell Lystrosaurus is kind of like the bulldog of early reptiles. He definitely is not an ocean swimmer, but Lystrosaurus is also found on continents that are now separated by huge oceans, Africa, India, and Antarctica. Certainly this guy was not going to be swimming across oceans to migrate from Africa to India or from either continent to Antarctica. So it is, again, more likely that Wegener's observation that the continents were once together and Lystrosaurus could just kind of wander among these different continents rather than swim oceans. The other thing that Wegener noticed too is that if you put the continents back together, he noticed that there were matching geologic units. So for example, you would see that rocks found in this part of Africa would match up very nicely with rocks that would have been in contact with that region if you had reconnected South America. Same thing too, rocks of certain ages, right? These kind of green layers here that are found in South America would match up really nicely with the green layers that would have been in Africa if the two regions had been connected. So 500 million year old rock units, these really old Archean rocks, right? And mountain belts, right? That's what these kind of wavy lines are here. These little mountain belts would match up perfectly, but only if you put the continents back into the supercontinent of Pangaea. There's our matching. I didn't realize that I had another slide there. There's our matching mountain belts too, to bring it a little bit closer to home. Here's the Appalachians running across the eastern coast of North America, and there are matching mountain belts in Africa over here, showing that we actually had a similar mountain belt forming on both continents once Africa was once attached to North America. So Wegener kind of is putting all these things together in his mind, and he says, okay, cool, I've got this idea that the continents are moving. They were once all connected in this supercontinent of Pangaea, and the scientific community said, great, Alfred, that sounds like a really cool idea. What's your mechanism? How do you think the continents are moving? And how do you think that the continents are able to plow through the ocean floor? Wegener didn't really know. And so he actually came up with this idea that said, well, if the Earth is spinning, right, if the Earth is rotating, maybe the continents are plowing through ocean floor mainly just by the centrifugal force created by Earth's rotation. It was a good idea. However, lots of other scientists kind of did back of the envelope calculations and figured out that that mechanism was absolutely not possible. If centrifugal force was the reason for continents plowing through the sea floor, then the centrifugal force should have been enough to have people essentially being flung off the planet. And we know that that, of course, wasn't happening. So Alfred Wegener, believe it or not, died without knowing whether his hypothesis had any sort of scientific truth to it. He knew he had collected valid data, but because he didn't have an appropriate mechanism for what could cause the continents to move, he was actually ridiculed and, believe it or not, died without knowing whether the continental drift hypothesis would ever truly be accepted by the scientific community. I'm going to take a side jog here, and I want to talk about electricity, iron, and magnets. And you're going to think, okay, wait a minute, this girl's crazy. Why are we talking about electricity if we were just talking about Alfred Wegener in 1915? Bear with me for a second. Do you remember I said in the beginning of this discussion that we're going to use the geodynamo system to actually support plate tectonic theory? Well, the geodynamo system, I'm going to just write this down here, geodynamo. Okay, geo-earth dynamo is a self-perpetuating system, okay? So the geodynamo is essentially the generation of a magnetic field from within the Earth, and it is a self-perpetuating system. So we, as long as we have the same Earth systems happening, we will continue to make a magnetic field. How do we do this? Now, do you remember when you were in maybe middle school, you took a nail? Okay, so here's my iron nail. You kind of can't really see it because it's white, but there's an iron nail. And what you did is you wrapped a wire around it. And so you kind of take just a piece of wire, you wrap a wire around it. And you take that wire and you attach it to a battery. And what will happen is that once you attach both ends of the wire to the battery, you now are sending an electrical current through the wire and through the nail. And for a short time, you can actually make that nail magnetic. So an electrical current, right? Any electrical current sets up an electromagnetic field. So when the current carrying wire is wrapped around the iron, here I'll put nail, right? It creates an electromagnetic field. So you may have done this again in like earth science, but the important take-home message here is that electrical currents generate magnetic fields. Now, remember, what is an electrical current? An electrical current is just a flow of electrons. A flow of electrons, that's all we need is to set up an electrical current. Where can we get a flow of electrons? Well, we have a metal-rich, liquid outer core. That liquid outer core convects. Remember convection cells, right? We've got convection cells like this. So that liquid outer core convects, and that convection, the rising of hot stuff and the sinking of cool stuff, essentially just sets up a flow of electrons in the metal iron-rich outer core. So we set up this flow of electrons in the convecting outer core, and any flow of electrons generates a magnetic field. So, voila, Earth essentially generates its own magnetic field because of convection in the iron-rich outer core. So if we look at the image on the left over here, this is a diagram of Earth's magnetic field. So the magnetic field lines come out the south magnetic pole and they come in the north magnetic pole. And they're actually coming out in all directions, even out towards you and into the page and everything else like that. But as long as we have the continued convection in the Earth's outer core, we will continue to generate a magnetic field. Why is this important? We're talking about tectonics. Well, once we figured out that the Earth had a magnetic field, we actually could use that to help test Wegener's hypothesis of continental drift. So Earth has a magnetic field, and like I said, the magnetic field today shows that essentially magnetic field lines come out the south geographic pole and they come in the north geographic pole. We call this normal polarity, right? Normal as in it is the same as it is today. However, at times in geologic history, the polarity of the Earth has actually switched to where magnetic field lines come out the north geographic pole and come in the south geographic pole. Notice that the dipole magnet, right, the two-poled magnet has now switched. So at these times when Earth's polarity has been opposite of what it is today, we call that reversed polarity. So the orientation of Earth's magnetic field can and does reverse. It has switched between normal, like it is today, and reversed, like it has been before, polarity over 171 times in the last 76 million years. And it seems to be not cyclic. There's no cycle to it. It doesn't happen every 10,000 years. And I know what you're thinking. You're going to ask, wait a minute, Dr. L, why does the Earth's magnetic field switch? Great question. We don't know. I think we would give you an honorary PhD if you were able to figure it out, and people are actively trying to do that. We don't know why it does it, but we do know that Earth's magnetic field does switch between normal and reversed polarity. So hang on to that for a second. The other cool thing about Earth's magnetic field is that it does get recorded in rocks, and we have rocks pretty much throughout the entire history of the planet, all the way back to about 4 billion years or so. So magnetic minerals, right, magnetic minerals that have metals in them, when they are formed, they can align with Earth's magnetic field at the time that those minerals form. We can get magnetic minerals in sedimentary rocks, and we can actually get them in igneous rocks as well. For example, imagine that you had a lava flow and the lava flow oozes out onto the Earth's surface. What will happen is that lava flow, all the magnetic minerals in it will align themselves the same way with the same polarity as Earth's magnetic field is at the time that that lava cooled. If this happens throughout geologic history, as Earth's polarity is switching from, normal to reversed, you can actually record this in the rock record. So rocks can record whether Earth has a normal or a reversed polarity throughout geologic time. Once we figured out that Earth had a magnetic field, of course, scientists were very interested in testing whether the rocks everywhere on the planet recorded the same magnetic signature. What they did is they took a boat, and they actually, off the back of the boat, they put a meter called a magnetometer. So literally, this little machine back here measures the magnetic orientation of the rocks beneath it. So let's say that right now, Earth's magnetic field is set up like this. Okay, let's say that we have normal polarity. Reversed polarity would be this way, right? This would be reversed. As the magnetometer moves over rocks, if the rock that it's going over has normal polarity, just like today's normal polarity, what you will see is a signal showing normal polarity. However, if the magnetometer is going over rocks that have a reversed polarity in opposition to today's normal polarity, you will see actually a negative anomaly. You will feel less of a magnetic pull because the rocks at depth are showing the opposite magnetic signature. So what happened is that the magnetometer was pulled along the ocean floor, and every time the magnetic signature was recorded by the magnetometer, it would show during times of normal polarity a positive anomaly, because both Earth's magnetic field today and Earth's magnetic field recorded in the rocks both show the same direction. And whenever the rocks underneath the magnetometer showed a reversed polarity, here you would see a negative anomaly because Earth's polarity was showing this orientation, but the rocks were showing opposite. Now this was actually really important because lots of people thought that since all of the ocean floor was made of the same rock, it probably formed all at the same time, and they assumed it would have all the same magnetic signature, but it didn't. This was kind of weird, and so people started to get curious about why does the ocean floor show essentially very different shapes of rocks that have different types of magnetic polarity, both normal and reversed polarity. Well, right around the time of World War II, the military started to develop sonar technology. Now, if you've ever used a fish finder or anything like that, you've used sonar. Essentially, a sonar will generate energy waves, sound waves, and it will send them down to the bottom of the sea floor. And it will then wait for those energy waves to kind of bounce off the sea floor, collect or listen for those sound waves, and get an actual image of what it looks like on the ocean floor. One thing that was very interesting during World War II was that the oceans were not just these flat, boring, featureless basins. What folks noticed during World War II as they were sonaring the entire ocean basins, they noticed that yes, there were very low, flat regions that they called the abyssal plains, where not a whole lot of topography is happening. But they also noticed that in the middle of the oceans were these big, tall mountain chains, and that those mountain chains were very long. They also noticed that on the edges of continents, right, here's the continent, there was kind of this gradual slope before you dropped off into the abyssal plain. Same thing on both sides over here. So they started to notice that there actually was quite a bit of topography, right? Lots of highs and lows, lots of mountain chains in the bottom of the ocean, and they didn't actually know why this occurred. So they started to investigate these a little bit more. They looked at the seafloor topography, and while this is vertically exaggerated, this is showing it kind of very dramatic, they did notice that, look, you've got these big, what they called mid-ocean ridges, right? Big high spots. There may be very kind of low abyssal plains. There may be these little kind of ridges or mountains, some of which actually popped up and made islands because it hit the top of the ocean. Some which didn't make it to the top, right? They looked like little mountains or islands, but they were under the earth, under the ocean. And that there were also these really, really deep, kilometers deep trenches. These places where there seemed to be, just tons of seawater in this deep ocean cavern. They noticed that those trenches, right? Noticed here, these are places where we've got big trenches. They're highlighted in purple. Those trenches usually were connected to other trenches, and that they were also long linear features. And they also noticed too that the mid-ocean ridges, right, these big mountain chains were also connected in this kind of sutured pattern all throughout the earth. So something was certainly going on here with all of these mid-ocean ridges and these deep sea trenches. When they measured the temperature over mid-ocean ridges, my shorthand over here, MORs, is mid-ocean ridges, they noticed that right over the mid-ocean ridge axis, it was very, very hot. So if this is the ridge axis right here, temperature is at its highest, but that it gets a lot colder as you move away from the ridge axis. Something was producing a whole lot of heat right underneath the axis of the mid-ocean ridges. Okay, so the mid-ocean ridges are very hot. They also noticed too that places where those mid-ocean ridges were found, remember I drew this very similar looking suture on the previous slide, right? All these orange dots are places where you have earthquakes. So a lot of places where you had mid-ocean ridges, but also trenches, were places where you had a lot of earthquake activity. We now know, of course, that earthquake activity is generated by the release of pressure, the release of stress as rocks move past each other. So there's definitely movement going on at mid-ocean ridges and at these trenches. So it all kind of came together with a World War II officer named Harry Hess. This is Harry Hess here on the right here's double H right here. And he's in front of one of his most famous drawings, which is essentially trying to put all the data that he collected during World War II together. Remember, they noticed the seafloor topography, that there were these big ridges, and then there were these broad, flat plains, and then these deep trenches. They noticed that it was hot over the ridges and very cold in the trenches. And what he also predicted was that the ocean crust was probably a lot younger. So the ocean floor was younger than the continents, and that because there was heat flow over the mid-ocean ridges is where new ocean floor, so new sea floor, was being made at the mid-ocean ridges. This is important, right? Because at the mid-ocean ridges, what he's showing right here is that this would be a mid-ocean ridge and that you would be now creating new sea floor and pushing the material away from that mid-ocean ridge. So Harry Hess's idea, I'm going to kind of shorthand it here, SFS, is sea floor spreading. His idea here is that the reason why mid-ocean ridges are hot is because there is rising material coming up from the mantle beneath. So this is the asthenosphere here. And that sitting above that asthenosphere are these very thick, rigid layers called the lithosphere. Okay, remember those layers that we talked about on the first slide? There's our lithosphere. And so the hot mantle material coming up at the mid-ocean ridges is trying to make new lithosphere, specifically ocean floor. Now, Harry Hess also knew that essentially the planet's seafloor isn't just getting bigger and bigger and bigger. The planet just doesn't make new seafloor in a continuum. We can form new crust at the mid-ocean ridges, but it's important to say that the old crust has to be consumed somewhere else. The place where Harry Hess suggested that crust was being recycled was in the trenches. This is where we could take very old and usually colder, more dense ocean floor, and we could actually send it back down into the mantle to get recycled. And then eventually it would come back up at a spreading center sometime later. So seafloor spreading meant that new crust forms at the ridges, old crust gets recycled at the trenches, and essentially the seafloor is spreading. So Hess decided, okay, I'm going to test this. How could we test this based on the observations of what we know of Earth science in the 1960s? Harry Hess remembered the idea about magnetism and the seafloor. And so what he did is he looked, if this is the mid-ocean ridge axis right here, he looked at the magnetic signature of rocks on both sides of the mid-ocean ridge. Specifically, he wanted to look at the magnetic signature of seafloor rocks. If the arrow is showing white, that means normal polarity, and if the arrow is showing black, it's showing reversed polarity. What Hess noticed is that as he moved away from the mid-ocean ridges, in either direction, rocks forming on either side of the mid-ocean ridge recorded the same changes in magnetic signature in a matching barcode on either side of the mid-ocean ridges. What that means is that the rocks forming here, right, formed at the same time. The rocks formed here formed likely at the same time, and that these rocks here formed at the same time, but everything is being pushed away from the mid-ocean ridge as new material keeps pushing up and making the seafloor spread. So this is the idea here of seafloor spreading thanks to Harry Hess, and it makes a whole lot of sense that we've got now convection in the asthenosphere, right? You've got convection cells in the asthenosphere because the asthenosphere is fluid, right? Convection here. And what happens is that convection in the asthenosphere creates motion and it moves the rigid lithosphere on top. And that is what creates the movement of our plates. The lithosphere, I'm going to use a different color here. The lithosphere here has the crust sitting on top of it. So lithosphere essentially is the rigid uppermost part of the mantle plus either continental or ocean crust. Places where you have ocean crust, right, the lithosphere and the crust is very thin. Places where you have lithosphere and continental crust, it's much thicker. But either way, convection in the asthenosphere is going to push lithospheric plates and create the mechanism that Alfred Wegener couldn't figure out for continental drift hypothesis. A couple of years later, in the late 1960s, I'm just going to erase all of my little arrows here. In the late 1960s, folks decided they were going to really test this idea of Hess's seafloor spreading. And the Glomar Challenger, which is a large ocean research vessel, went out and it actually took up cores of the ocean floor. To validate Hess's idea of seafloor spreading, they did notice that indeed the age of sediment increased. So sediment got older as you went away from the mid-ocean ridge axis. So if you have a ridge like this, right, this stuff was old out here, and this stuff was young closest to the mid-ocean ridge. That supports Hess's idea of seafloor spreading. The other thing that they noticed is that sediment above the seafloor actually got thicker as you got farther and farther away from the ridge axis. What that meant is that as you moved away from the ridge axis, sediment sitting on top of the ocean floor got thicker as you moved farther and farther away. That meant that this crust had been sitting around for a lot longer to get sediment deposited on top of it than the brand new crust forming at the mid-ocean ridges. The other cool thing that they found with the Glomar Challenger was that the oldest ocean crust is only about 200 million years old. So, okay, pop quiz, how old is the Earth? Okay, it's about 4.6 billion years. Okay, 4.6 billion years old. But the oldest ocean crust is only about 200 million years old. What happened to all of the ocean crust older than 200 million years? Well, what seems to be is that Hess's idea of recycling of old ocean crust in the trenches is actually true. All of the old crust, older than 200 million years, has been subducted in the trenches and has been recycled back into the upper mantle. So pretty cool, right? We see that the age of the ocean, this is a heat map, and this is just showing you essentially, excuse me, I'm calling it a heat map, it's not temperature. What's showing you is the age of the seafloor. The hotter the color, the younger the age of the ocean crust is, and the colder the color, the more blue, the older it is. What you notice is that right at the ridge axes, right, here's all of our mid-ocean ridge axes, right here, you have all the very young crust, the new stuff being formed, and only the farthest away from the crust, from the mid-ocean ridge, excuse me, do you have the really old crust here. And that crust is usually entering a subduction zone. For example, there's a very big subduction zone over here on the left, and that's where that Pacific Ocean crust is going to be recycled. So, okay, so now we have this idea of a plate tectonic system, and it started with Wegener's continental drift hypothesis and really only became validated in the 1960s once we understood that the convection currents that were setting up in the upper part of the mantle, right, in the asthenosphere, are what's going to then move our plates. Now, let's remind ourselves what convection is. Remember that as you go deeper and deeper and deeper into the Earth, it's going to get hotter. Okay, so it's hot down here and it's cool up here. So what tends to happen is that things that are hot will rise, right? So just like, you know, a flame sitting here on a Bunsen burner, you will actually have hot stuff rising and cold stuff sinks. So hot material is less dense and it rises. Cold stuff is actually more dense and will actually sink. So these convection cells that we're making in the asthenosphere happen because mantle is hot at depth, and because it's hot, it is now low density and it rises. As that mantle hits the cold lithosphere sitting up here, it transfers its heat and it cools down. It starts to move laterally, all the while transferring its heat to the lithosphere. And eventually, as it cools down, it becomes more dense and it starts to sink back down. This creates the convection currents of the asthenosphere. So these convection cells in the asthenosphere match up very nicely with where we think plate boundaries are with respect to things like mid-ocean ridges and deep sea trenches. Where you have mantle coming up to the surface is where you would have two convection cells coming together and you'd make a mid-ocean ridge. Where you have cold asthenosphere sinking back down, going back down into the mantle, that's where you would get these trenches where you would get subduction zones. So we create convection cells on which the lithospheric plates move around. So remember, we have different types of upper mantle material, right? We have the lithosphere and we have the asthenosphere, and the asthenosphere is fluid and the lithosphere is rigid. So you can think of this as like kind of cold and rigid, but the asthenosphere is kind of warm, convecting, and behaves more like a fluid. So these are both considered parts of the upper mantle, But the lithosphere contains the crust, both continental crust and ocean crust. It's important to remember that we have different types of crust. So you have continental crust here and you have ocean crust here. Ocean crust is very thin. Continental crust is thick. However, continental crust sits up high, whereas ocean crust kind of sits down low. Ocean crust is very thin, but it is what we call mafic. It has lots of iron and magnesium, so it is dense. Continental crust, on the other hand, is thick. It's made of felsic materials, which are more aluminum and potassium rich, and so it is less dense, and that's why it sits up high. We can actually support this by the principle of buoyancy, right? That the continental crust essentially sits up high, not only because it's less dense, but that thickness is what really helps us. We have a really thick bottom part of our continental crust. We call this a root, right? The continental crust has a thick root, and that root is actually pushing away the mantle, and that displacement of the mantle beneath the continents creates a sense of buoyancy, right? Creates a push that then helps the continent to sit up high. The principle of buoyancy is very similar to what you would see with icebergs, right? If you see an iceberg, right, you only have about 20% of the iceberg visible on top of the water, but there's a lot more of it sitting beneath the water surface. And it's this 80% beneath the water surface that's helping to displace the water, that's helping to keep the iceberg buoyant. It's the same idea with thick continental crust. Because we have now lithospheric pieces, rigid, cold lithospheric pieces at the Earth's surface that are moving around thanks to convection cells in the asthenosphere, we can actually now differentiate about 13 major lithospheric plates. And so I'll put up here major plates, but these are actually lithospheric plates. And so just for reference, right, you are here on the North American plate. But notice too that we have our North American plate boundary way over here in the middle of the Atlantic Ocean. So we sit on the edge of a continental boundary right over here, right? There's the edge of our continent, but our continent is very far from its plate boundary. The eastern edge of the North American plate is what we would call a passive continental margin. What that means is that the edge of the continent does not coincide with a plate boundary. And so we don't have a lot of earthquakes or volcanoes. We're a relatively passive situation. Compare that, though, with the western coast of the North American plate, where you have the continental margin coinciding with a plate boundary right here. This is what we call an active continental margin. An active margin is where you have a continental margin that is sitting on a plate boundary. Of course, this is where you would also see a lot of energy release, like earthquakes or volcanoes. This would be a good place to take a break if you wanted. We only have about, I don't know, 15 or 20 more minutes to go. But if you wanted to take a break and kind of stretch, wander around the room, do something like that, why don't you do that now, and then we'll come back and we'll remind ourselves of the three main types of plate boundaries that we can find around the lithosphere. Okay, if you've chosen to stick with me, that's great. We'll still talk about our types of plate boundaries, and we'll go ahead and finish up today's lesson. You might remember from your 1101 class that there are three main types of plate boundaries. Now, all the plate boundaries that we're going to talk about right now are going to be active plate boundaries, right? This is where we're going to be talking about things actually happening in terms of activity like volcanic activity or earthquake activity. But let's talk about these three different types. Our first one is a divergent plate boundary. What does it mean to diverge? It means to essentially spread apart. So at a divergent plate boundary, it means that two pieces of lithosphere are separating. What is the effect of that? Well, it's a constructive effect. That means we're making new oceanic lithosphere here. What do we find in terms of features there? Well, we create mid-ocean ridges there, and that's if these divergent plate boundaries are in the ocean, you make a mid-ocean ridge. But if you actually have two plates separating and it's on a continent, you create something called a rift. For example, the East African Rift is where the African continent is separating. Do we have volcanic activity at divergent plate boundaries? Absolutely, right? Because we've got mantle material coming up to the surface here. So yes, we definitely get volcanoes there, and we also get shallow earthquakes. So the next one we're going to talk about is convergent plate boundaries, right? Convergent is where you have two plates now coming towards each other. So they are converging. The motion that we have there is coming together, and it will usually involve collision or subduction. I'm going to actually change this, subduction or collision, right? The reason I'm saying that is because if two plates are coming together, the one that is more dense will tend to sink beneath or subduct beneath the other one. So usually what happens is when two plates come together, the one that is more dense will be the one that subducts. If you have a piece of continental crust and a piece of ocean crust is more dense, so it will do the subducting. If you have two pieces of ocean crust, right, ocean crust convergence, excuse me, which one will sink? Well, the one that is more dense. Now, how do you know which ocean crust piece is denser? I'm going to give you a little trick. Older, colder, denser, deeper. Okay, if you can remember this, the one that will do the sinking is the older one because it's the colder one. It's the colder piece of lithosphere, and colder material is denser, and so it will be the one that sinks deeper. Okay, so older, colder, denser, deeper will actually help you remember which piece of ocean lithosphere will do the subducting. So those are usually pretty easy to figure out. However, what happens if you have two pieces of continental crust coming together? Well, neither one of them is more dense than the other. In fact, they're both very buoyant. So when two pieces of continental crust come together, instead of making a subduction zone, you make a mountain chain. So that's why I wanted to annotate this to say that you can have, in a convergent boundary, you can have subduction or you can have collision, especially if you have two continental land masses coming together. So this is usually a very destructive type of plate boundary, right? You're either kind of destroying stuff by making mountains, or you're actually consuming, subducting ocean crust. So what's the topography there? We'll either get trenches or we'll get mountains. And do we have volcanic activity there? Absolutely. Most often you get volcanic activity when the subducting ocean crust gets deep enough, it will start to melt. And that melted material is hot and less dense, it will rise up to the surface and will create a volcano. Last but not least, we're going to now talk about transform plate boundaries. Okay, our sense of motion here is lateral sliding, so literally plates are just kind of slipping past each other. And therefore the sense of motion is conservative. There's no crust either being created or destroyed, and so there's no major topography there. You may not get volcanoes, but you'll notice you do get earthquakes. A great example of a transformed plate boundary, of course, is California, and we know California has lots of large earthquakes. So here's a couple of images of each of these types of plate boundaries. You should be able to notice that this is a divergent plate boundary. First of all, notice that the arrows are showing that the two plates are moving away from each other. So we're making new lithosphere here, and we're pushing the old lithosphere away. In this situation, since we're in the ocean, we're creating a mid-ocean ridge. Everywhere you see on the map here that is colored in red, the really young sea floor, these are all mid-ocean ridges. So here's a Jeopardy question for you. What's the longest mountain chain in the world? It's actually not anything on a continent. It's actually the mid-ocean ridge system. These are all mountains associated with each other, and they're all connected by forming new oceanic lithosphere. You can, however, get a divergent plate boundary underneath a continent. So notice that we've got our sense of motion pulling apart here. Over time, pulling that continent apart will end up making a very thin region in the middle, and we call this a rift system here. So for example, in East Africa right now, the eastern part of the continent looks a lot like this, where you have very thin crust because it's being pulled apart, and you have a lot of volcanic activity in the middle part of the rift. In several hundreds of thousands to maybe millions of years, what will eventually happen to the African continent is that the two parts of the plate will continue to pull apart, and eventually you'll make a new ocean basin in the middle of the African continent. So those are divergent plate boundaries. Here's an example of a convergent plate boundary. So you'll notice that we've got here's our lithosphere, right? The big packages, these are here. Here's our lithosphere, our overriding plate. Here's ocean crust sitting on top of the lithosphere here. Here's continental crust sitting on top of the lithosphere over here. And here is the subduction zone with the oceanic crust on the lithosphere down, kind of subducting down underneath the overriding, more buoyant continental crust. As this lithospheric plate works its way down into the mantle, you will actually start to get melting of that plate. That melt is very hot, and it will start to rise up, and you'll create volcanoes here on the overriding continental plate. You'll notice once again, I've listed on the bottom here, older, colder, denser, deeper, and that's how we're going to remember which plate will do the subducting when you get to a convergent plate boundary. Remember, only ocean crust is going to subduct. Continental crust is too buoyant. Convergent plate boundaries are actually very easy to image if we map the location and depths of earthquakes. As plates start to subduct, they will eventually start to then get kind of sucked down into the mantle. All the while, the subducting plate is kind of releasing energy as it is moving further and further down into the mantle, and every time it slips a little bit and moves a little bit, it will give off an earthquake. Earthquakes are just energy release, and so if we measure the location and depth of earthquakes, what we notice is that if all these little asterisks here, right, are the location and depths of earthquakes, there is a zone that is about 700 kilometers deep into the earth where we see earthquakes that are showing that the subducting slab is still moving down beneath the overriding lithosphere. So this 700 kilometer thick zone is called the Wadati or Benioff zone. So the Wadati zone, here we go, tells us essentially it's the zone of earthquakes that is created by the descending plate as it's moving down through the subduction zone. What we notice is that below about 700 kilometers, there are no more earthquakes. Why do you think there's no more earthquakes as you get deeper and deeper into the earth? Think about what happens as you go deeper. It is really hot down here, right? So stuff starts to melt once you get below about 700 kilometers. So you get a lot more fluid movement, and you're not able to create earthquakes like you did when you were up in the cooler, more upper parts of the mantle. And so now you can also get at convergent zones. Remember, here's a subduction zone, right? Here is our ocean crust ooh, that looks like an E. I want ocean crust, but here's continental crust, right? Both on the same slab of lithosphere. As this lithospheric plate moves down, it's going to consume the ocean crust in the subduction zone. But watch what happens when we have those two plates moving together. We've chewed up all the ocean crust, right? There's the sinking oceanic lithosphere. But once the pieces of lithosphere came together that had continental crust on it, neither one could subduct. So instead, we get a collision zone where we essentially now have two continental land masses coming together, and we make mountains. We make mountains when two pieces of continental crust come together because, remember, continental crust is too buoyant. It can't subduct, and so both pieces of continental crust kind of get smushed together and uplifted to make mountains. India is moving northwards right now. India is a continental landmass, and it is moving northwards into the Asian continental landmass. And if you look at the boundary of the two right in here, this is where you get the Himalayas. So you're seeing a beautiful example of two colliding continents and the resulting mountain chain because neither one of them can subduct. So India moving north, Asia moving south, and then the huge chain of really high mountains forming in the Himalayan plateau right between the two. Now we also know the Himalayas are actually getting higher and higher each year at a small amount, but they are still increasing. And that has to do with the fact that the two plates are still colliding, still trying to push those mountains rather further and further up. Last but not least, we've got our transform plate boundary, and I don't want you to get confused. The arrows in this GIF right here are not the transform plate boundary. What are the arrows showing? The arrows are showing divergence, right? So that's not the transform plate boundary. The transform plate boundary usually is found, at least in a mid-ocean ridge system, between two divergent boundaries that are moving at different speeds. So this is actually why the mid-ocean ridge systems have kind of that, like, it looks like a sutured look almost, like it looks kind of like stitches or something like that. What's happening is that you've got divergence away from this ridge, but notice you've got another ridge axis over here, but maybe you've got divergence at a different speed over here. And so right in between the two, right just in this region here, you have a little zone where these two plates are moving past each other at opposite directions. This arrow shows that this piece of crust is moving to the right, but this arrow is showing that this piece of crust is moving to the left. So this little zone right here is a good example of a transform plate boundary. They happen around mid-ocean ridges, but they don't always have to form near mid-ocean ridges. They can also form in other places, and we know this, right? For example, here's the San Andreas Fault. So this is kind of a neat situation. Do you see what I just animated here? This is actually, oh, it won't let me go back. That's not nice. This is actually the fault plane right here. This is the San Andreas Fault, and the movement along the fault is this way, right? This pink line here is actually a river. And the river used to be a straight line, but now movement on the San Andreas Fault has actually moved the river to have kind of an S pattern like this due to the kind of side-by-side motion there. Remember, no crust is being formed and no crust is being consumed. You're just having lateral side-by-side movement here. You can notice the offset a lot of times when you have linear features like a river like this or mountain chains or something like that. You can see the offset associated with transform plate movement. Okay, so the last two little tiny things I want to cover in today's lesson, and then we'll be done pretty quickly, is the mechanisms that are behind plate movement. Remember we talked about how Alfred Wegener had this idea that continents were moving, but he didn't really have a good mechanism to explain how the continents were moving with respect to, say, for example, the sea floor. Then came along plate tectonic theory, and plate tectonic theory says that we're making new crust at the mid-ocean ridges, we're consuming old crust at the trenches, and that it's convection in the mantle, that specifically the asthenosphere, right, the fluid upper part of the mantle, that is helping us to move the cold, rigid lithosphere plates. Geoscientists aren't sure right now whether the convection in the mantle is essentially in whole mantle convection, meaning that the entire mantle is one humongo convection cell like this, or whether it is stratified convection, meaning that there might be convection cells down here in the mesosphere and then other convection, smaller convection cells in the asthenosphere. So we haven't actually proved this 100%. I think a lot of data seems to support this stratified convection. But so the major driving mechanism of plate tectonics is mantle convection. And whether it is whole convection or stratified, again, the jury is out, but mantle convection is kind of the main driving force. So mantle convection here is the main driving mechanism. Remember, the asthenosphere is where we're getting that convection, and it's going to create two physical forces. By forces here, I mean literally vectors, right? Things that you could actually draw a line on in, say, physics or something like that. As the new material is being pushed up at the mid-ocean ridges, right in here, right? Here's the mid-ocean ridge. New material keeps getting pushed up behind it. And so as we make new seafloor, the only way we can accommodate more mantle material coming up into the ridge is to push the old material away from the mid-ocean ridge. So that's our first vector called ridge push. We're pushing the old lithospheric material away from the mid-ocean ridge as we create new stuff during seafloor spreading. At the other end of our lithospheric plates, in subduction zones over here, at subduction zones, this is where we get our second force called slab pull. As that subducting slab starts to move into the trench, remember, this is an old and very cold and very dense piece of lithosphere. Imagine that this is, I don't know if I can draw an anchor, but you know what I mean, right? This is actually behaving like an anchor. So the pull of this old slab is exerting a vector of pulling towards the subduction zone on the rest of the lithospheric plate. So the subducting slab exerts a vector of pull on the rest of the plate, pulling the lithospheric plate towards the subduction zone. So ridge push and slab pull are the two physical forces that result from mantle convection, and they are really the driving forces behind plate tectonics. So you can kind of see how over the last 100 years or so, we morphed from Alfred Wegener's idea of continental drift hypothesis, which, you know, had some good points to it, but actually his mechanism turned out to be incorrect. And so we revised, we retested Wegener's continental drift hypothesis, added more data and observations to it. Remember, we're using the scientific method, adding all that information from World War II and Harry Hess to say that we have seafloor topography, we've got the magnetic barcodes on the ocean floor, we see lots of heat flow over the mid-ocean ridges, we see mid-ocean ridges coinciding with earthquake and volcanic activity. All that information now leads us to plate tectonic theory, which seems to have been repeatedly tested, and the observations continue to support the theory of plate tectonics, which suggests that it is convection in the mantle. Again, whether it's whole mantle convection or stratified, we don't really know, but it's convection in the mantle, which actually causes rigid, cold lithospheric plates to move around the Earth's surface. And where they interact with each other, you get different types of plate boundaries, specifically convergent, divergent, and transform plate boundaries. So this is the end of the material for our first week of classes. This is where the material for Monday's quiz stops. And you'll notice that the review sheet is already posted on As You Learn for Monday's quiz. And so you can go ahead and review that. As always, if you have any questions, please don't hesitate to get in touch with me, especially if it's before Monday's quiz if you have any questions. Have a great weekend, guys.